Today we are going to do some examples. Example 4 and example 5. These two examples are supposed to be a little bit more challenging and difficult than the ones that we did in the last lecture. So why don't we start with this one, example 4. So in this example, we are supposed to find the double integral of x over a domain region. Okay, at the start here, we know right away that x is the function that we are supposed to find the double integrals on. So we also know that this function is in terms of variable x and y. Even though you don't see y here, you know that these variables are related to Cartesian coordinate. So the function that is given to us is in Cartesian form. Cartesian. Alright, and then it says that the domain region is bounded by some lines here, or you can say curves. So we have the first line, which is the x squared plus y squared equal to 2x, and then the next one, y equal to x, or you can say x equal to y, is the same line, and the last line is x-axis. Okay, 3 lines here, 1, 2, and 3. Okay, in this example, we are supposed to use the polar form. Actually, you can try to solve these double integrals by using the Cartesian form, but using the polar form is going to be more convenient. So let's see if that is true. So we are going to use the polar form. Okay, that is our focus in this chapter, polar form. And as you know, the polar form has its own formula when it comes to double integral, and it looks like this. The double integral of a function. Of course, this is polar form. It means that the function has to be in terms of radius and theta. Now, the following terms is the differential area, or dA, and in polar form, this is equal to r dr d theta. I am not going to explain again why r dr d theta is equal to dA in polar form, because we did that in the last video. If you are not sure about why it's equal to dA, you can watch the last lecture again. Okay, so this is the formula. Now let's take a look at the order of the integration. You can see that here we are going to integrate with respect to r first, and then with respect to theta. So when we integrate with respect to r, we are going to sweep the radius, and the radius has to start from one function that is called g1 theta and ends at another function. You can think of this function as the line or the curve. Alright, this is theta. Okay, g1 theta is the start of the radius sweeping, so you can say that this is start of radius sweeping, and g2 theta, that is the end of the radius sweeping. Okay, the next integration is with respect to the theta. So theta starts from some value, and we call that alpha, and ends at another value over the whole range, ends at theta equal to beta. So we are going to use this formula. It means that we have to find this new f, g1 theta, g2 theta, alpha, and beta. Once we find all of them, we can start doing the integration right away. But to find them, it's very difficult without seeing the graph, without seeing the region. It's almost impossible to know how to sweep the radius and how to sweep the angle. So when it comes to double integrals, most of the time we start by drawing the domain region. I think it's the same for the examples. For all the examples that we did so far, we start by drawing the domain. Alright, so the first thing here, the domain. Now we have to take a look at all these 3 lines that's going to define the domain. 1, 2, 3, and let's skip 1 for now because that one is tricky. So let's take a look at number 2, which is y equal to x. This line is easy. We know that this is a straight line with a slope of 1 passes through the origin. Now x-axis is easy. It's easy to draw. The only problem here is this: x squared plus y squared equal to 2x. Why? Because so far we have seen curve like this: x squared plus y squared equal to some constant square. And with this kind of form, you know that this is a circle of radius r. Easy to draw. But then the equation that we have here is this: x squared plus y squared equal to 2x. We got something different right here. So we can't draw this by using this equation directly. So let's work on this equation a little bit more to make it more manageable in this problem. So from the equation that we have, I am going to move that 2x right here to the right hand side of the equation. So here I'm going to have x squared. I move 2x over here, it becomes minus 2x. I leave some tiny space right here, and then I leave plus y squared just like the same. And then on the right hand side, this becomes 0. Same equation. Only 2x is moved to the left hand side. And then I add this term, plus 1, on the right hand side and on the left hand side. Still same equation, right? So with this parenthesis, you can do something with this equation. Alright, with the parenthesis terms, you can see that this is equal to x minus 1 square plus y square equal to 1. Okay, this form, you can see that this is like a variable square plus another variable square equal to a constant square. This form is very similar to the circle equation. Alright, except that we have this minus 1 extra terms right here. And I think many of you can tell by now that this is also a circle with radius 1, except that it's shifted to the right 1 unit. So this is graph shifting, something you learn from maybe high school or middle school, I don't know, from long time ago. But as you can see here, this is equation of a circle, except that it's shifted to the right 1 unit. So let's make a note on that. Circle of radius r, but shifted to the right 1 unit. Right. So with this information, I think we can start drawing the graph now. So let's put everything in the graph so that we can see the domain region. Alright, y-axis. Okay, and this is 1, and right here 2. Now circle of radius 1. Oh, this is not radius r. Sorry, let me fix that. Of radius 1 shifted to the right 1 unit. It means that the center is no longer at the origin. It's moved to 1, 0 right here. So we are going to have a circle with radius 1 right here. Alright, that is the first line. And then the next line is y equal to x. So we have this straight line. Alright, and then the last line is x-axis. So let's combine them and find all the boundaries. The first one, x-axis. Next one, y equal to x. And the last line is the equation for the circle. And we know it's shifted to the right 1 unit is this. So all these boundaries defined the domain region, and it looks like this. Okay, so with this in our hand, we can start to look for all these 5 terms in the formula: f, g1, g2, alpha, and beta. So let's put some label here. So the first thing we are supposed to find is this function f in terms of radius and theta. But what is given to us is this f equal to x. And we cannot use x just like this. We are supposed to change x from Cartesian form into polar form. And from last time, we know that the relation between x and r and theta is x equal to r cosine theta. In the last lecture, we proved why this is equal to each other. So if you forgot about that, you can watch the previous video. So now our function is in terms of radius and theta, so good to go. Now we are supposed to find g1 theta and g2 theta. This is about how the radius is sweeping across the region. Now let's take a look at this region here. The radius is going to start from the origin and sweep to the circle. Origin to the circle, origin to the circle, origin to the circle, all the way through. So let's put this into words. So radius r sweeps from the origin 0, 0 to the circle. Alright, now we know the starting point and the end point here. So here, this is going to represent g1 theta. Circle here represents g2 theta. Now let's take a look at g1 theta right here, which is the origin. So let's focus at the origin. You take a look here at the origin. In terms of radius, what is that value? Right at the beginning, and it doesn't go anywhere. Right here, it means that radius is equal to 0 at the origin. Okay, so which means that at 0, 0, radius equal to 0, which means that g1 theta is going to be equal to 0. Okay, so now we got the g1 theta. Now g2 theta is going to be this line, which is on the circle. This circle is represented by the equation, the first one that is given to us. So this is x squared plus y squared equal to 2x. But we cannot use this equation as g2 because g2 has to be in terms of theta. So we are supposed to do something with this equation and make it into a polar form. And from the relation that we found from the last lecture, we found that x squared plus y squared equal to 2x. Right here, we can transform it. This equal to r squared. And x here equal to r cosine theta. So with this, we can see that r squared equal to r, don't forget 2 right here. We have 2 r cosine theta coming from this equation. Alright, it seems like we can cancel some of the r's. So here we have r equal to 2 cosine theta. And this is the equation for the circle. Same thing. This equation, same as r equal to cosine, forgot 2 again, 2 cosine theta. Same equation, same curve, except that is in different form. One is in Cartesian and the other is in the polar form. Alright, so g2 theta in terms of r, it's going to be equal to this. Alright, so we can say that in terms of radius, g2 theta equal to 2 cosine theta. Alright, g1 theta right here and f is right here. Now, we need to find alpha and beta. We need to take a look at how the theta, or the angle, sweep across the region. And look at this. You can see that angle starts from the x-axis and sweep to this y equal to x line. X-axis, y equal to x line. Sweep like this. And from the look of this, you can tell that the angle that y equal to x makes to the x-axis, this is 45 degrees, which means that the theta is going to sweep starting from alpha equal to 0, which is the x-axis, and ends on the y equal to x, which means that beta is going to be equal to pi over 4, and that is y equal to x line. Now we have all these 5 terms. Everything. It means that we are ready to put all these terms into the formula. So let's take a look at the complete formula. Okay, integration double of the function in terms of radius and theta, and that is equal to r cosine theta. We found it up there, right? Times r dr d theta, that is dA, and radius starts sweeping from radius equal to 0 and ends at g2 theta, that is 2 cosine theta. Now for the theta, sweep from 0 and ends at pi over 4. After this, it's all about doing the integration. Okay, so let's continue from that. So let's combine r together, that is r squared. Cosine theta, double integration, 0 to 2 cosine theta. And with respect to r, now with respect to theta, starting from 0 to pi over 4. Okay, so we are going to integrate this with respect to r first, and then we are going to treat theta as constant. Alright, so integrate this with respect to r only. We are going to get r cubed over 3. Alright, cosine theta doesn't change because it's constant in this case, at this point. And we have to evaluate this at two values, r equal to 0 and r equal to 2 cosine theta. And we integrate this one more time with respect to theta. From 0 to pi over 4. Alright, 2 cosine theta goes in. So I'm going to get 8 cosine theta cubed over 3. Alright, well, let me change this. I want to save some space. So 2 cosine theta goes in as r, so you get 2 cubed, that's 8. And cosine theta cubed divided by 3, the term that we had before, times cosine theta. Minus 0 goes in, and you can see 0 goes in, everything goes to 0. 0. And we are supposed to integrate this with respect to theta from 0 to pi over 4. Alright, let's put an equal sign here. This is going to be equal to, now I'm going to take the 8 over 3, the coefficient, this outside, so it's easier to integrate without that. So 8 over 3 comes outside, integrate from 0 to pi over 4 of cosine theta to the 4th, d theta. Okay, at this point, I think you should know that when it comes to trigonometry with some power like this, it's not going to be easy to integrate directly. Right? Trigonometry with power, not easy to do it directly. And it's recommended that you try to reduce this power to be 1 if you can. Alright? Try to reduce power to 1. If you can do that, the integration would be much easier to perform. So let's use some property that we learned from trigonometry class. So we learned that cosine theta squared equal to 1 plus cosine 2 theta over 2. This is from long time ago, maybe from high school or maybe from middle school, I don't know. But this has been proven and we are going to use it. So here we are going to use this to evaluate cosine to the fourth. We want this. We want cosine theta to the fourth. And we try to reduce this power of 4 to 1 somehow. So this is going to be equal to cosine theta squared times cosine theta squared, right? And we are going to use the first equation and substitute that to here. We have 1 plus cosine 2 theta divided by 2 times the same thing, 1 plus cosine 2 theta. I'm going to take the 1 over 2 out, so 2 of them becomes 1 over 4, and the inside this, I'm going to combine them. So front and 2 front back plus back square cosine 2 theta square. Alright, it looks a little bit better. It used to be 4. And then we reduce it to, okay, the first one is already a power of 1, but we still have this power of 2 here. So we are going to do something extra here. So we are going to use this cosine 2 theta square is equal to 1 plus cosine 4 theta over 2. Alright, we are going to substitute this into this term. So what do we have here? We have 1 over 4, 1 plus 2 cosine 2 theta plus 1 plus cosine 4 theta over 2. Now to make this look easier to manage, I'm going to take 1 over 2 out. This becomes 1 over 8. This becomes 2 plus 4 cosine 2 theta plus 1 cosine 4 theta. Right, combine everything, we have 1 over 8. 3 plus 4 cosine 2 theta plus cosine 4 theta. And that is equal to cosine theta to the fourth. We are going to substitute this into here. Alright, so let's do that. 8 over 3. I hope we have enough space here. So 8 over 3 integrate from 0 to pi over 4. Now everything goes in here. Alright, so we have 1 over 8. Okay, 1 over 8. 3 plus 4 cosine 2 theta plus cosine 4 theta. Right, integrate this with respect to theta. It seems we can cancel this. Okay, let's continue with this. So 1 over 3 is still out here, and integrate 3 with respect to theta, it becomes 3 theta. Integrate 4 cosine 2 theta, it's going to become 4 sine 2 theta divided by 2 because of the reverse chain rule. Now integrate cosine 4 theta, you are going to get sine 4 theta, right? Diff sine, you get cosine. You integrate cosine, you get sine. And then don't forget to put divide this by 4 because of the chain rule backward. Right? Now, you have to evaluate this at 0 and pi over 4. Okay, we are running out of space, so I'm going to erase some of this part up here. Okay, now let's put everything in. So pi over 4 goes in. This is going to be equal to 1 over 3. Just the same, pi over 4 goes in. This becomes 3 pi over 4. Pi over 4 goes in here, becomes pi over 2. So we get plus 4 over 2 sine pi over 2. Okay, and pi over 4 comes in here, goes in here. This becomes pi. So we have this plus sine pi, all right, over 4. Now minus, all right, okay, minus 0 goes in. This is going to become 0. Plus 0 goes in here, sine 0, sine 0, plus 0 goes in here, becomes sine 0 again. Well, you can keep this 4 over 2 right here and this divided by 4 right here, but it doesn't matter because you know that this goes to 0. Goes to 0. Sine 0 is 0. 0. Sine pi also 0. So in the end you have this term 1 over 3 pi over 4. So this term becomes 2. Sine pi over 2, that is 1, so plus 2. Plus 2. So in the end we have this pi over 4 plus 2 over 3 as the final answer for this example. Okay, so the idea to do this, the whole idea is to draw the domain region and find out how to sweep the radius and how to sweep the angle. And after that, it's just the integration like you did before. Okay, let's move to example 5. Okay, example 5, we are supposed to change this double integration, and you can see that they give us function in Cartesian coordinates. So they give us f, x, y. Right? They want us to change this into a polar integral. Supposed to change this into polar form and then evaluate this. Okay, polar form. Once again, we are going to use this function in terms of r and theta. r d theta. Radius from g1 theta to g2 theta. Angle from alpha to beta. Okay, so just like before, all these examples, you are supposed to see the region. Without seeing the region, you don't know how to sweep the radius and the theta. So we are supposed to look at this double integration in Cartesian form and try to get the domain region out of that. So let's take a look here. Let's take a look at the double integration here. So you can see that, So you can see that y is the first variable that we are going to sweep here. So y start from 0. Y sweep from 0 to what? To this function y equal to square root of 1 minus x minus 1 square. Alright, that is the information we have. And x start from 0. and ends at 2. X sweep from 0 to 2. We need to translate this into a diagram. We need to find out what shape of this domain region looks like. So y sweeps from y equal to 0. Let's take a look here. Y equal to 0. Y equal to 0 is the same as x-axis. Alright, so we are going to draw this graph right here. This y variable is going to start from this x-axis right here. X-axis. Then it sweeps to this equation y equal to square root of this 1 minus x minus 1 square. Well, looking at this, it's kind of hard to determine the shape. So why don't we do something with this? Let's square both sides. So this becomes y squared equal to 1 minus x minus 1 squared. So the inside of the square root comes out. Now let's move things around. So here we can see that this is equal to x minus 1 square. I move these terms on the right hand side to the left hand side, plus y square equal to 1. Well, does this look familiar to you? Well, it should be, because we just saw this from example 4, and this is equal to, this is going to be a circle of radius 1 shifted to the right 1 unit, shifted because of this term. So let's draw that graph right here. 1 here, 1 here, and this is a circle of radius 1. Okay, and we also need to keep in mind that y equal to square root of this whole term. It means that y has to be positive. Y has to be greater than 0. Okay, information, y starts sweeping from x-axis to this circle of radius 1, and y has to be positive. So what's going to happen here is that y is going to start sweeping from x-axis to the circle, x-axis to the circle, circle, continue. And how do we know the range of the whole sweeping here? So we have to take a look at x, and we can see that x starts sweeping from 0 to 2. X equal to 0 here, x equal to 1 here, and 2, which means that we are going to sweep this y all across x from 0 to 2. So we have this region as the domain region in this problem. So let's put the boundaries here. That is the circle, and that is the x-axis. Okay, now that we have this domain region drawn on the diagram, we can start finding all these terms for the polar formula. So we are supposed to find f. Okay, now we can find it here. Let's use the space right here. We are supposed to find f in terms of r and theta, but it's given to us in this form: x plus y over x squared plus y squared. We cannot use this. We want r and theta. So let's transform this into polar coordinates. X equal to r cosine theta, y equal to r sine theta, x squared plus y squared equal to r squared. So in the end, we have this cancel, r right here and square right here. So we have cosine theta plus sine theta over r as the function. Now we need to look for the starting and the ending of the radius sweeping. Now we have to come back to the diagram and determine how the radius sweep across the region. Radius start from the origin, sweep to the circle. Start from the origin, sweep to the circle, sweep to the circle. So we can make a note here. R, sweep from origin to circle. Alright, and as you can see here, is the same shape as the last example. In terms of radius, the origin is r equal to 0. And for the circle, same circle as last example. This circle is the same as r equal to 2 cosine theta. If you wonder why this is equal to 2 cosine theta, we explained about this right here. Same thing here. Same curve, which is the circle of radius 1 shifted to the right 1 unit. Alright. Same as last example. So this curve right here, circle right here, r equal to 2 cosine theta. Alright, which means that g1 theta, which is the start of the radius sweeping, is equal to 0. And g2 theta, the end of the sweeping on the circle, that circle is r equal to 2 cosine theta. Alright, now about alpha and beta, we have to take a look here. It's going to be different from the last example. Alpha starts from x-axis and it sweeps anti-clockwise all the way to y-axis. All the way to here, y-axis. It might look a little bit different here. It might look that it doesn't go to pi over 2, but the whole range right here it starts from alpha equal to 0 to beta equal to pi over 2. So you can say right here that alpha equal to pi, alpha equal to 0, alpha equal to 0, and beta equal to pi over 2. Okay, we have all these terms. Let's combine them and complete the formula. So from the formula, in double integration, alright, alpha start from 0 to pi over 2. Now for the g1 theta, start from 0 to g2 theta equal to 2 cosine theta. Function right here, this is equal to cosine theta plus sine theta divided by r times r dr d theta. And we can see here that we can cancel this r. Maybe we got lucky here. Okay, r here cancel. Now let's continue from this. Double integration, alright, of cosine theta plus sine theta. We are going to integrate this with respect to r first and then with respect to theta. R from 0 to 2 cosine theta, and theta from 0 to pi over 2. You know, this is quite similar to example 4 except some terms, the function and beta values. So the rest of this is all about the integration. So let's do the integration here. Alright, so you take a look at this. We are supposed to integrate this with respect to r. Here we only see theta, so treat them, these terms, as constant. So here this is going to be equal to constant cosine theta, that's a constant, so integrate with respect to r, so r shows up. Sine theta, constant, so r shows up in front of that. Alright, and we are supposed to evaluate this at r equal to 0 and 2 cosine theta. Right, integrate this one more time with respect to theta from 0 to pi over 2. Alright, 2 cosine theta goes in here and here. So what do we have? We have 2 cosine theta square plus 2 cosine theta goes in here. It becomes 2 sine theta cosine theta. And now for 0. 0 goes in here, becomes 0. 0 goes in here, becomes 0. So after this, this is 0. And we are supposed to integrate this with respect to theta from 0 to pi over 2. Right, you see something different here. Here you see trigonometry with some power and product of trigonometry. If you do this directly, it's going to be difficult. So the best way is to try to make this to have power of 1. Right, as you can see here, 2 sine theta cosine theta, it's possible to make this becomes just one term, and that is equal to sine 2 theta. Okay, so looking at this, 2 cosine theta squared, this is equal to 2 cosine, oh no, this is equal to cosine of 2 theta plus 1. Okay, so let's continue from that. Cosine 2 theta plus sine 2 theta plus 1. We are supposed to integrate this with respect to theta from 0 to pi over 2. Alright, at this point it should be easy. So integrate cosine 2 theta, it becomes sine 2 theta divided by 2 from the chain rule backward. Integrate sine 2 theta, it becomes minus cosine 2 theta divided by 2. Integrate 1, this becomes theta. We have to evaluate this at 0 and pi over 2. Okay, I'm going to continue right here. Alright. Okay, pi over 2 goes in. Right, this becomes sine of pi over 2 minus cosine of pi over 2 plus pi over 2. Now I have to minus with 0 goes in, 0 goes in, and 0 goes in. This becomes sine 0 over 2 minus cosine 0 over 2 plus 0. Let's evaluate these terms. Sine pi, that's 0. Cosine pi, this is 1. So we have this minus 1 over 2. Alright. Oh, cosine pi, this is equal to minus 1. Sorry, minus 1, so this is equal to plus 1 over 2. Plus pi over 2 right here. Minus. Alright, so we have this sine 0, that is 0. Cosine 0, this is 1. So we have minus 1 over 2 right here. So the answer at the end becomes pi over 2 plus 1. Final answer for example 5. So we can see the similarity between example 4 and example 5, except that the only difference is that here in example 5 they give you the function and the domain region in form of the double integration. Right? They give you the domain region right here at the integration sign, but up here they give you the domain region. For example 4, they give you the domain region right here. Right. But in the end, in terms of computation, it comes out to be the same.